Hello everyone, my name is Tuan from CS in Schools, and I'm here today to go through a sample solution for question 2 in the sample written examination for specialist mathematics. And this one will be focused on pseudocode. So in this question, we are provided with a procedure below, and it's been supplied in pseudocode. The output of the pseudocode, we've been told, is going to be a list of numbers, and we're asked to find the final number in that list. So the way we're going to tackle this is we're going to start by constructing a trace table, which you can see there on the right-hand side of the screen. Now, if you want some more information on trace tables, please check out our successful pseudocoding course and playlist. You can find the link provided. So the way we're going to step through this problem is we are going to go through each line of the pseudocode one at a time, and we are going to update the trace table on the right-hand side there. So the first line is saying declare integer n. What that means is we're going to create a variable called n, and we're going to slot that into our trace table there on the left-hand column. What we're going to do next is then progress one line at a time through the pseudocode and update our trace table. So the next line is saying declare integer f. So just like the first line, we are going to create a new variable and put that there on the left-hand column. Declaring integer t1 is the third line. Similarly, we're going to put in t1 and then declare integer t2, and there is t2. So the first 4 lines of pseudocode is about constructing, declaring, creating variables which we've captured there on the trace table. So the next 4 lines of pseudocode are where we are going to initialize those 4 variables. So initializing means we're going to set them up with some initial or starting values. So that line there is saying set f to 0. So all we're going to do there is put in the value of 0 in the value column that is next to the variable on the trace table. Next line is setting t1 to 2. So you can see there 2 has been assigned to t1. Assigning means taking the value and putting it into that variable. Setting t2 to 3. There's 3 next to t2. And then setting n to 3. And there's 3 next to n. The next line is getting us to set up a loop. So a loop is a special construct in pseudocode that allows us to repeat certain segments of code. So in this line, you can see there's a couple of new words here. We see the word repeat. And what that means is that we're going to repeat the next set of 3 lines that have been indented. That is, it's been pushed in and underneath the repeat keyword. So everything that's been indented and pushed underneath the repeat keyword and is between the word repeat and end loop, that's going to be repeated. And you'll find an expression that comes after the repeat keyword, which will indicate to us how many times to repeat that section of code. Here we see the variable n, and so that's indicating to us how many times that will be repeated, and we'll talk about that in a second. So in order to work that out, we're just going to consult our trace table, and we see that n has a current value of 3. So when we see an expression that involves a variable, what we're going to do is take the value that corresponds to that variable and substitute it in for that expression. So what that means is we are going to repeat that section of code 3 times, as indicated by the value in n. So when we are repeating that code chunk, we're just going to go through one line at a time from top to bottom as we have previously. So let's take a look at that first line that's been indented. Here we see it's f equals t1 plus 2 times t2. So when we see the equal sign in pseudocode, it's similar to how we might understand the equal sign in maths. But there's a subtle difference which is important to keep in mind. When we see the equal sign in pseudocode, we must always look at the right-hand side first. So we evaluate the right-hand side, we evaluate that to a certain number or certain value, and then we assign that, or we put that into the variable that we always will find on the left-hand side of the equal sign. So here we're going to look at the right-hand side. We're going to evaluate it using the standard rules of BODMAS. So we've got T1 plus 2 times T2. All we do here is we look up each of the variables in that expression and we substitute in the value that is inside that variable. So T1 is substituted for 2 and T2 is substituted for 3. So then we can evaluate that using BODMAS. We find that is 8. And then we can take 8 and assign that back into the f variable. So what happens now is the f variable will change from 0 to 8. It's important when you're constructing the trace table to cross out the original number and write in the new one so you can keep track of the values that are changing for that variable. So that's the first line done. We're going to move to the second line. The second line is a simple expression. It's just taking f and assigning that into T2. So this is why it's super important to run the pseudocode one line at a time, because you saw here the previous line changed the value of f. So when we follow it one line at a time, we will know that when we get to the second line, we're going to use the new value. That's why we shouldn't rush when we are processing pseudocode. It's super important to go through it one line at a time. So here we take the 8, we substitute it in, and then we assign it into the T2 variable. So T2 now has changed from 3 to 8. And then the last line of code here inside that block is saying printf. Now, print is a special command in pseudocode that will always be followed with an expression of some sort. And what print does is it evaluates that expression, so it works out the final value, and then it displays it onto the output. So in this case, the expression is just a simple variable, f. So whenever we find a variable in an expression, we take its latest value, we substitute it in. So that's basically saying print 8. So what happens is 8 gets displayed on the screen. So what we've done now is we've gone through those 3 lines of code and we've finished one iteration because they form that chunk of code that's been indented. We're going to keep track of the number of times we've repeated as an extra variable in our trace table, just keeping in mind that we are aiming to repeat this 3 times. So we've repeated that section of code once. We now go back up to the top and repeat it a second time. So let's go back up again and we'll go through this again a little bit more quickly. So we have that f equals T1 plus 2 times T2 expression. We substitute in the latest values of those variables. We find that's 18. We assign that to f. So f changes from 8 to 18. We move to the next line, which takes the latest value of f, which is 18. Substitute that into T2. So 8 becomes 18. And then we print f. Now f is 18, and the slight difference with the print command is that it preserves what is previously displayed on the output. So as opposed to variables changing values, the output is displayed underneath the previous value. So we see both the original output and the new output underneath it. Okay, so that's our second iteration. So we're going to go back and repeat that one last time. The first line there is f being assigned to T1 plus 2 times T2. So f gets updated to 38. We move to the next line. T2 is assigned that value of f. So 38 gets put into T2. We're going to display the value of f on the screen. F there being 38, and then 38 appears on the screen. We're going to update the number of times we've repeated. So now we've reached the third iteration. We've repeated 3 times now, so the whole loop is done. So we go to the next line of code. There are no next lines of code, so the algorithm is done. Now let's just review the question there. The output of the pseudocode is a list of numbers, and we can verify that it is indeed a list of numbers, and it's asking us for the final number in the list, and that number is 38. So that's how we complete that question. If you require some more assistance with any of the concepts we've covered so far, please feel free to check out our website, csnschools.io, and there's a pseudocode course there that you can check out that provides more exercises for you to go through. Thank you. Hello everyone, my name is Tuan from CS in Schools, and in this video we're going to go through a sample solution for question 5 in the Sample Written Examination 2 for VCE Specialist Mathematics, and it is focused on pseudocode. In question 2, it says the algorithm below, described in pseudocode, estimates the value of a definite integral using the trapezium rule, and we are provided with an algorithm in pseudocode. It then asks us to consider the algorithm implemented with the following inputs, and then asks us to find the value of the variable sum after one iteration of the while loop. So if you haven't already, please watch the first video in this series as it covers some of the pseudocode concepts that we're going to go through in this video. And also, please check out our successful pseudocoding course for additional information and exercises. You can find that at csinschools.io/pseudo. So here is the pseudocode that they've provided for us. And this question involves the concept of a function in pseudocode. Let's quickly compare how a function works in pseudocode with how you might understand it in mathematics. So consider this function in mathematics. F of x is equal to x squared plus 4x plus 3. So this function has a name, and the name of the function is f. This function also contains a parameter, and in this case, the parameter of this function is x. And the function has a body, which is x squared plus 4x plus 3. Now, these three terms are going to also be applied to the concept of a function in pseudocode. Altogether, this is called the function definition. And in mathematics, to evaluate the function for a value, we can say that we call the function with a specific argument. So let's say f of 3. So the 3 in that case is the argument. And what happens next is that we take the value of the argument and we substitute it into the parameter that we see in the function definition. So what this means is we take the 3, we substitute it in for x, and that means anytime we see x, we use 3. So let's take a look at how functions work in pseudocode, and you can see that there's a lot of similarities. So in this case, we have a function that's defined for us, and the name of the function is trapezium. And you can tell what the name of a function is because they are the letters and symbols that you find before the brackets. And these are the parameters of the function. In this case, we have 4 parameters: f of x, a, b, and n, and they are separated by commas. The body of the function in this case is a lot bigger than the x squared plus 4x plus 3 example that we saw before. In this case, it involves many variables, it involves assignments, it involves a loop there, but it's still considered the body of the function. And altogether, the whole thing is called the function definition. So to evaluate the function, we call the function with specific arguments. So we use the name, just as how we did it before with f of 3. We're going to use the name trapezium, and we're going to fill it in with 4 parameters in this case. Here we have sine of x, 0, 10, and 100. And what happens next is we take those arguments' values and we substitute it in for the parameters in the function definition. So f of x takes on the value of sine of x, a takes on the value of 0, b takes on the value of 10, and n takes on the value of 100. So let's go back to the question here. We are asked to consider the algorithm implemented with the following inputs. So those inputs are basically the arguments. We are going to call the trapezium function as indicated by its name. These are the 4 argument values that we are supplied. So what we're going to do is substitute them in for the parameter variables in our trapezium function. So how we're going to handle that is we're going to construct a trace table. And once again, please refer to the previous video where we introduced you to trace tables in the context of these questions. So what's going to happen is we're going to take the parameters in the function definition and set them up as variables on the left-hand side of the trace table. So you can see there f of x, a, b, and n have been constructed as rows for themselves, and they have been filled in or initialized with the arguments that were used when we called the function. So the first argument was the natural logarithm of x, so that gets assigned to f of x. The second argument is 1, so that gets assigned to the second parameter of a, and similarly b gets assigned to 3, and n gets assigned to 10. So having set up those variables, we are now ready to go through our function one line at a time and see what happens. So in the first line, you see this little back arrow. So in pseudocode, sometimes the back arrow symbol and the equal sign are used interchangeably. They both indicate assignment. The previous video discusses how assignments work, but generally you always look at the right-hand side first, you evaluate the expression, and then you assign it into the variable that you always find on the left-hand side. So let's do that now. We're going to set this up as a new row in our trace table. The variable h has been inserted, and the entire expression has just been put into the value column for now, b minus a, all divided by n. So what happens is we're going to substitute the values for those variables using what we find in the trace table. So b gets substituted for 3, a gets substituted for 1, and n gets substituted for 10. So we plug them in, we evaluate it to 0.2, and that will be the final value that we assign to h. So that line is done. We move to the next one. So here we find that sum is going to be assigned the value of f of a plus f of b. So let's set that up in our trace table and begin to evaluate the expression on the right-hand side. So f of a plus f of b, what we're going to do is substitute in a and b into those function calls. So that's f of 1 plus f of 3. Now we know that f, the function, is the natural logarithm of x when we consult the trace table above. So that's really saying the natural logarithm of 1 plus the natural logarithm of 3. So if we evaluate that with our calculator, we arrive at the value of 1.099 to 3 decimal places. So that will be assigned to the value for sum. The next line is a plus h is going to be assigned to x. So there's our x variable, a plus h, substitute in our values, and we get 1.2 being assigned into x. And then we just have 1 being assigned to I, so there's I and 1 right there. So now we come to this next line of code, which is another loop. So you may have remembered us using the repeat loop in the previous video. This one is a slightly different kind of loop called a while loop. So the way that a while loop works, it's similar to how a repeat loop works in that the code that is indented and underneath it will be the section of code that will be repeated. So you can see that code there highlighted in red. However, unlike the repeat loop, there isn't a predetermined number of times in which we will repeat the code. So we don't know in advance how many times we're going to repeat that section of code. So to determine whether or not we repeat the code, we always look at the expression that follows to the right of the while keyword. So in this case, it's I less than n. And that expression will always evaluate to either true or false. So let's see what that gives us. So let's plug in the values. I is substituted by 1 and n is substituted by 10. We now have the expression 1 is less than 10. Now that expression will only give us a true or false answer. In this case, 1 is less than 10, so it's true. Now when the expression after the while statement is true, we are going to go inside the loop and execute the indented lines of code. So it's true, so we're going to go into the indented block of code. And just like in the previous video, we're going to go through the lines of code one at a time. So let's do that. So the first line of code there is assigning sum plus 2 of f of x into sum. So let's substitute in our values. Sum we had from before, which is 1.099. F of x, well, x is substituted by 1.2, and f is substituted by the natural logarithm. Plug that into our calculator, and correct to 3 decimal places, the answer is 1.463, and that gets assigned back into sum. So you can see there the sum value has changed. The next line of code is updating x. It's adding h to x and then assigning that back to x. X is 1.2, h is 0.2, so the answer is 1.4. That gets assigned back into x, and x is updated to 1.4. And then the last line of code there is adding 1 to I and assigning that back into I. So that's 1 plus 1, which is 2, and then that goes back into I, so I goes to 2. Now, the last 3 lines of code illustrates why the assignment operator in pseudocode is not the same as the equal sign in maths, even though they are related. Because let's take a look at that last line and rewrite that and consider it from a mathematical point of view. I equals I plus 1. Now, that's clearly not correct from a mathematical perspective, unless if I was infinity, of course. So it's just a small point to keep in mind that in pseudocode, the assignment operator is not the same as the equal sign. Anyway, so we've done those 3 lines of code. We've just completed 1 iteration of the while loop. And if we consult our question again, it's asking us for the value of the variable sum after the 1 iteration of the while loop. So we've done the 1 iteration, so we can now arrive at our answer. So let's look at the variable sum, look at its value, which is 1.463, correct to 3 decimal places, and that will be the final answer to the question. Just to wrap up this little session, if the question didn't ask us to stop after 1 iteration, what that would mean is the code would continue. And in this case, with a while loop, when we've finished the indented line of code, we would always go back up to the while condition and we would re-evaluate that Boolean expression. And in this case, if we were to do that, we would see that I has now changed from 1 to 2. 2 is still less than 10 if we plugged in those values, and so that condition is still true. And while that condition is true, we're going to go back into the loop and repeat again. So even though the question is only getting us to do it 1 time, in general, the way the while loop works is that it's going to continue to repeat that section of code as long as that condition is true, or while that condition is true, hence the name while loop. So we'll go through an example with multiple iterations another time. Thank you for listening to this video. Once again, please jump onto our website, csinschools.io, for additional content and materials around pseudocode. Hello everyone, my name is Tuan from CS in Schools, and I'm here to go through the sample solution for Written Examination 2, Question 6 for VCE Mathematical Methods Units 3 and 4, and this is focused on pseudocode. So question 6 is saying, considering the algorithm below, which uses the bisection method to estimate the solution to an equation in the form of f of x is equal to 0, and then they give us the algorithm there. The algorithm is implemented as follows: bisection sine of x, 3, 5, and 2. What value would be returned when the algorithm is implemented as given? So if you haven't already, please watch the first 2 videos in this series as it covers pseudocode concepts, which we assume you already know. And as usual, please check out our successful pseudocoding course for additional information and exercises. You can find that at csinschools.io/pseudo, and that's PSEUDO. Okay, so let's go into the question. It's saying that the algorithm is implemented through the calling of the bisection function. So what we're going to do here is, yes, we can see that section calling the function, and we can see that in between the brackets, we have 4 values. And if you can recall, those 4 values are the arguments. That's the bisection function up the top there. And so what happens next is that those 4 argument values are going to be passed into the function parameters. And all that happens is that those parameters get substituted by the values that we call into. So to get started, we're just going to create a trace table here, and the 4 parameters are going to be set up as variables on the left-hand column, and their values, they're going to be the values of the arguments that are being passed into the function. So we see here f of x will take on the value of sine of x, a will take on the value of 3, b will take on the value of 5, and max will take on the value of 2. So let's go through line by line in the function and execute this and see what we get at the end. Now, it's important to note that in this question and the questions we had seen previously, we don't actually need to understand how the bisection method works. All we're asked to do is, given the algorithm, run through it, and then record the answer that is popped out. So we're just going to step through the algorithm as given without necessarily explaining how it works. We assume that that will be covered in your standard mathematics lessons. So the first line of code here is an if statement, and it's checking to see whether if f of a times f of b is greater than 0. So to evaluate that condition, what we're going to do is pop those expressions into our trace table there, f of a, f of b, f of a by f of b. So the next step is to substitute the variables with their values. So f of a and f of b become f of 3 and f of 5, and f of 3 by f of 5. So if we evaluate those, given that the f function is sine of x, and we pop that into a calculator, we find that f of 3 by f of 5 is equal to negative 0.135, correct to 3 decimal places. So we're going to substitute that back into our expression there, and we can see that we're just checking if negative 0.135 is greater than 0. So it is not greater than 0, so that condition is false. And if you recall, when the condition in an if statement is false, we skip to the next unindented line underneath the if statement. So we do not run that return invalid interval line there. So we skip to the third line in our function, where we are going to take 0 and assign that to I. We pop that into our trace table. Then we get to a while loop. So the way that the while loop works is it's similar to an if statement in that the condition that follows the while statement must be evaluated and checked to see whether it's true or false. If it is true, then we enter the while loop. So let's evaluate that condition there. So while I is less than max, so let's substitute in I and max. So we get 0 is less than 2, which is true. And being true, we are going to enter our loop, which means we're going to execute the next line of code that is indented and underneath the while statement. So that line there is going to assign a value into mid, that being a plus b all divided by 2. So there it is. Let's plug in the values, and we get mid being equal to 4. So that gets assigned into the mid variable. The next line is going to check to see whether f of mid is equal to 0. So let's check that. F of mid is f of 4, and f of 4 is sine of 4 because f is sine. Let's evaluate that. That becomes negative 0.757. Is that equal to 0? That's definitely not equal to 0. So that's false. So when that if statement is false, we jump to the next unindented line, which is else if. We're going to ask a follow-up question to see whether this second question is true. The condition in the second question is true. So that one is f of a by f of mid is less than 0. So let's evaluate that. F of a is f of 3, f of mid is f of 4, f of a by f of mid. Once we substitute in a and mid, we get negative 0.107. So we substitute that back into that expression, negative 0.107. Is that less than 0? It definitely is. So in this case, we'd enter the if block, which means we execute the lines of code that are indented and underneath the if statement. And all that's doing is assigning the value that is in the mid variable into b. So that means b changes from 5 to the value that was in the mid variable, which is 4. What happens next is that last else statement is skipped, because that last else statement only runs if all of the if conditions above it is false. It's kind of like the final safety net. Okay, so since the second else if was true, we can disregard the remainder of that if block and we go to the next unindented line of code, which is I plus 1 goes into I. So all that does is it increases the value of I from 0 to 1. So then we reach the end while. So contrary to what that word may indicate, we have not finished the while loop. What end while means is that we go back up to the condition and we reevaluate it. Okay? So we go back up and we reevaluate that while condition, and if it's true, we go back into the while loop. We do not go to the next line. So end while does not mean we jump to the next line and we're finished with the while loop. The only time we're done with the while loop is when that condition is false. So end while just means go back up, reevaluate the condition. Only when it's false do we end. If it's true, we go back in. So let's go back up, reevaluate that condition. Now we see that I has gone up from 0 to 1. 1 is still less than 2, so that's true. So the next line is we go into the while loop and we go again the second time. So let's go through, reevaluate the mid value. So mid will then now change to 3.5. We're going to look at f of mid, which is f of 3.5, which is sine of 3.5, which is negative 0.351. Is that equal to 0? It is still not equal to 0. That's false. So we're going to do the follow-up if statement. F of a by f of mid. That turns out to be negative 0.049. Is that less than 0? Yes, it is less than 0. So we go into the if statement there, which updates b once again. So it takes mid, which is 3.5, puts it into b. So b is now changing from 4 to 3.5. We jump to the end of the if block where we increase I by 1 again. So I now goes from 1 to 2. We reach the end while loop, remembering that when we get to end while, we go right back up to the top and we re-evaluate the condition. So here it's 2 is less than 2. Is that true or false? 2 is not less than 2. It's actually equal to 2. So now that condition is false. And being false, we can now end our while loop. So that whole while loop is finished. So we go to the next unindented line that's underneath the while statement, which is return mid. So what return means is that whatever value follows return or whatever expression follows return will be given back to whatever called the function. So here we've got return mid. So let's evaluate mid. All that means is we just take the value, 3.5, and that will be the answer that we get after we call that function. So to answer the question itself, which value would be returned when the algorithm is implemented as given, the answer will be 3.5. So one last thing to clarify before we wrap up, notice that there are actually multiple ways that this algorithm can be completed. So there are 2 ways that I'm going to talk about here, and there's a third way at the end that I'm going to show you. So in our earlier walkthrough, we saw that that final return at the end there, this return here, that was the statement that finished our particular walkthrough of the algorithm. But you'll see that there's another return up here. So if you look at this situation, you can see that this return gets triggered if this statement is true. So that statement is true only when f of mid is equal to 0. So in that case, what that's saying is we have arrived at an exact answer to that problem. Remember, the bisection method is used to find the solution to the equation in the form of f of x is equal to 0. So if f of mid is equal to 0, then mid is going to be the exact answer. So if we ever reach this point, we know that we've gotten an exact answer to that question. However, if we reach down here, all that means is that we have gone through all of our cycles, our iterations. We haven't quite hit the exact answer, but this is our best guess after that many number of iterations. So those are the 2 ways in which we can end the algorithm with a value. There is another alternative, which is here, where we can return from the algorithm without a value. And in this case, this occurs if f of a by f of b is greater than 0. So what that means is if we had a graph that looks like this, so in this case, what that's indicating is the two endpoints that we've selected, A and B, those 2 points do not contain the crossing of the graph through the x-intercept. Okay, so normally, in order for this algorithm to work, we need to have A and B on both sides of the crossing so that we can arrive at the answer there. But in the case where we supplied an A and B, say for instance we put A over here and B over here, that would not result in an answer because there's no value in between A and B where the function f of x crosses the x-axis. So in that case, we would get this invalid interval. So the way that the algorithm determines whether A and B do not contain a crossing is it's looking at the sign of f of a and f of b. So this would only occur if f of a is positive and f of b is negative, or f of a is negative and f of b is positive. That means we've crossed over, either going that way or either going that way. So if the signs of f of a and f of b are the same, that means they're either both positive here or they're both negative here. That's what this line of code is doing. It's checking whether the two signs are the same by multiplying them together. And remember, if the two signs are the same, multiplying them together will give you a positive value. So we're looking for the case when the two signs are different. So multiplying them together should give you a negative value. So if you do multiply them together and you get a positive value, then it means they're on the same side and you would get an invalid interval being returned from the algorithm. So that's how question 6 works out. It's a little bit of an explanation at the end for how that first invalid interval occurs, but by stepping through the algorithm, you can see how the final answer of 3.5 is obtained. If you are an Australian secondary school student or staff, you can go to our website csnschools.com or csnschools.io for more information about the courses and offerings that we have. Hello, I'm Tuan from CSN Schools, and in this session, I will be walking you through a sample solution for Written Examination 2, Question 7 for VCE Mathematical Methods Units 3 and 4. This one is also focused on pseudocode. So Question 7 is saying that one way of implementing Newton's method using pseudocode with a tolerance level of 0.001 is shown below. The pseudocode is incomplete with 2 missing lines indicated by an empty box. They've given us some code there, and which one of the following options would be most appropriate to fill the empty box? So this question is a little bit different from the other pseudocode questions that we've gone through previously, in that this one does require us to understand how Newton's method works and how to actually represent that in pseudocode. The other questions previously, we were given the pseudocode and we were asked to find the final value. So you didn't really need to understand what the pseudocode is doing. You just need to be able to follow it through line by line. But in this case, we do need to understand how the pseudocode will implement Newton's method. So the way I'm going to walk through this solution is I'm just going to give you the answer. So that's what the answer should be. And then I will walk through the algorithm and explain why that is the answer, and also give you a bit of a recap as to how Newton's method works in pseudocode. As usual, if you haven't already, please watch the first 3 videos in this series, because it does go through some pseudocode concepts that we are assuming you already know, and check out our successful pseudocoding course at csnschools.io/pseudo, PSEUDO, for more information and exercises. So we're going to step through the solution with some example arguments being passed into the function parameters. So here is, at the bottom there, the function Newton being called with some example arguments that I have created that we can use to step through the algorithm with. As usual, the arguments will be passed into the parameters, so they will get copied into the parameters, and we're going to step through the function with those values. The value for f of x I'm going to use is going to be a cubic. That's y equals x cubed minus 3x squared plus 3x minus 3. And that's just a visualization of what that cubic looks like. And remember that Newton's method is to find or to estimate the x-intercept of a function. So if we plot that function out and we take a look at it, we can visually estimate that it's between 2 and 3. It's sitting there. So what we're going to do is in the second argument to the function call, I'm going to start that off with the value of 2. So as usual, the parameters get set up as variables in the trace table. Their values get populated there on the right-hand side, and then we are ready to commence our step through of the algorithm. So the first line is asking us to find out the derivative of f of x. So what we're doing here is we're going to manually find the derivative and assign it to that variable df of x. So there it is, it's 3x squared minus 6x plus 3, using the standard rules for differentiating a polynomial. The next line of code is assigning 0 to I. Now, you may have noticed a pattern with the other questions before. I is typically used as a variable to keep track of the number of iterations that we go through a loop. It's generally a clue as to what I is going to do. Doesn't always have to be the case, but in these set of questions, they are following that rule. So 0 is being assigned to I, and then x naught, which is the initial estimate that we are starting with, which was 2 in this case, that's going to be assigned into the variable previous x. So there's 2 being put into previous x. So now we're going to enter our while loop. So as before, what we're going to do is we're going to evaluate the condition that follows the while loop. So we take the value of I, which is 0, substitute it into there, and then we check whether that condition is true or false. So 0 less than 1000, yes it is. So we are going to enter the while loop. And that's where we get to this line of code, which is getting us to calculate the next value of x. So we start off with x, the x-intercept, our guess of the x-intercept being 2. This line here is going to refine our guess using that formula there. Now, this formula is the heart of Newton's method, so I'm going to spend a bit of time just explaining visually what that means. So our function there is x cubed minus 3x squared plus 3x minus 3. And our initial estimate is going to be 2. So that's where previous x is. So what happens here in Newton's method is we are going to evaluate the function at that x value. So that yellow dot is indicating what the evaluation of that x parameter is. So that's where it sits on the curve. And that's at previous x and previous y. What's going to happen next is Newton's method will calculate the derivative of the function at that x value. So by calculating the derivative, that is forming a tangential line that touches the function at that point. We're going to use that tangent line, extrapolate it, and find out where it intercepts the x-axis. So that's at that red dot there. And that is going to be the next estimate for the x-intercept that we're going to use. So let's just go through the maths here so that that equation makes a little bit more sense. We're just going to focus on that red straight line. So we're going to look at how we can represent that using a straight line equation. So using y equals mx plus c, our traditional straight line equation, the m, which is the gradient for that equation, is essentially the derivative of the function at previous x. Okay, so we've just replaced m with df of previous x. The y-intercept is going to be 0. So that equation basically becomes y equals df of previous x, x. So that's one form of that red straight line equation. So the other equation can be obtained using the rise over run approach using the next and the previous points. So y equals mx plus c. M can be broken down as next y minus previous y, all on next x minus previous x. Now next y is going to be 0 because that's the x-intercept, so the y is going to be 0. Previous y is the function evaluated at previous x. So that's where we have previous y equals negative f of previous x. And the run is just next x minus previous x. And then we have the x afterwards. And once again, the cut or the y-intercept is at 0. So we can simplify that down into y equals negative f of previous x, all on next x minus previous x, x. So these two equations are the same. They're describing the same red line. And so we can equate the two gradients together. So we can pull them out and set them aside at the bottom there. And if we rearrange that equation so that we express everything in terms of next of x, because that's what we're trying to find, isn't it? We're trying to find what the next estimate of x is going to be. So we're going to rearrange all of the unknowns so that we can find what next x is. We get next x is equal to previous x minus f of previous x divided by the derivative of f at previous x. And if we extract that formula out, we can see that is exactly what is represented there in the pseudocode. So that's an explanation of that line of pseudocode. In a sense, that's the most important line in this pseudocode, but luckily for us, that was not the line that we had to know in the question that was being asked of us. But anyway, so that's how we evaluate next of x. You can see that is now popped into our trace table on the right there. We are going to evaluate that by plugging in 2 for previous x. Okay, we're going to substitute in the function and the derivative of the function, and we end up with next of x being 2.333. So what happens now is we're approaching the 2 lines of code that we needed to fill in to complete the algorithm. So let's take a look at that first line, and I'm just going to focus on the middle expression there between the 2 less than signs. So we're looking at the expression next x minus previous x. So if we evaluate that, it's 2.333 minus 2. And what that's doing is it's telling us the gap between the next value, the next estimate that we calculated, and the previous value. What's that gap? And we find that gap by taking away the previous value from the next value. Okay, so that's what that point is. What's the gap? What's the movement? Notice that this can be negative. It doesn't always have to be positive, because next of x can also be on the left-hand side of previous x, which we'll see in a later iteration. Okay, but just note that that can be negative as well, and it's okay. So we're just going to take that answer, substitute it into that middle expression there. And then the last part of that line is focusing on the tolerance level. So it's saying that we are given a tolerance level of 0.01. The tolerance indicates that the result is acceptable if the difference between the next and previous values, that is the gap, if that falls between plus minus the tolerance level. Okay, so the red area there is the gap. And if that gap is between plus and minus the tolerance level, then we are good and it's acceptable, and we can return that as an answer to this pseudocode. So if we evaluate that, we find that it is false, which means the gap is too large at this stage. Okay, the guess between our next guess is too far away from our previous guess for us to be satisfied that it's coming together. Okay, so it's not good enough. So we're not returning yet. Instead, we go to the else statement, and we are ready to move on to our next iteration. Okay, so we're getting ready for our next iteration here. So before we go to the next iteration, we are going to take our new estimate, next x, and we're going to put that into our previous x. So what that's doing, the new value of x is going to become the previous value of x when we go around the next time. Okay, so we'll show a diagram of that in a second. So this line here is taking the next value of x and putting it into the previous value of x. And you can see what's going on here, as the green dot is our next estimate, and that's going to be changed into the previous x for our next estimate. So there it is. Previous x is going to change from 2, which was our first guess. That will now become 2.333, a refined guess, and I is going to go up by 1, and then we reach the end while statement. So once again, end while doesn't mean we finish, it means we need to go back up and re-evaluate the while condition. So I is less than 1,000, is it? Well, I is now gone from 0 to 1. 1 is still less than 1,000, so that's true. That means we go back into our while loop. And now we're going to estimate our next value of x, using the previous value of x, which was the estimate from last time. So let's take a look here. Our previous value of x, that's the value of the function evaluated at that point. We're going to find the derivative of the function at that point, draw the straight line, find out where it intercepts the x-axis, and that will be our next estimate, which is next x. There's that equation again. So if we go through and calculate that, we get next x is equal to 2.264. Okay, so we come down to these two lines of code once again. We're going to calculate the gap between next x and previous x. Okay, so we're going to take previous x away from next x, and we get negative 0.099. So notice this time the gap is negative. If we go back and take a quick look at the graph, we can see that the green dot is to the left of the yellow dot, which means that the next estimate is less than the previous estimate. So that's where we can get a negative gap. Okay, so we take that negative value, we plug it into that expression there, and then we're going to evaluate to see whether that gap is between our tolerance level. It is not. So it's still not good enough. We're going to get ready for our next iteration here. And once again, we're going to update our previous x value with the latest estimate that we had. So there it is, changing to 2.264. We're going to update our I variable. So now we're in our third iteration. I is now going up to 2. We reach end while, which means we go back up and reevaluate our condition, which is still true because 2 is still less than 1,000. So then we go and we update our estimate once again. So let's go the third time. So here's our previous x, 2.264. Let's evaluate our function at that point and then draw the straight line graph and find out where it intersects our x-axis. We find it's 2.260. So there it is. X is 2.260. Let's reevaluate our gap. The gap is still not within our tolerance level. It's negative 0.004. And that's false in terms of falling within our tolerance level. So it's still not good enough. We go into our else statement. We get ready for one more iteration. Next x goes into previous x. I equals I plus 1. So that goes to 3. Let's go back up. 3 is still less than 1,000. We've actually got 997 times to go if we continue down this route. So we've got a long way to go in terms of the number of iterations. Let's go through and evaluate next of x once again. So there's 2.260. Let's evaluate the function at that point and draw a straight line and find out where it intersects the x-axis. We find that that's 2.2599. 2.2599, there it is in next of x. Let's calculate the gap. The gap is now 0.0001, which does fall between our tolerance level. So that's true. So that means that our gap is small enough now to be acceptable in terms of the algorithm giving an answer back to whoever called it. So what happens now is that we need to give an answer back. So what value is it that we want to give back? Well, we've really got two choices. We either will give back previous x or next x. We're going to give next x back because that is the more refined estimate that we calculated. So previous x was the previous estimate, next x is the next one, so we're going to give obviously the more accurate one, so that's why that line is going to be next x. So we're going to take the value, substitute it in, and then return that back out. So that's why those two lines of code are the way they are. So once again, if you'd like some more information about our coding courses, please check out our site at csnschools.com for more information about our company, and check out our site at csnschools.com for more information about our charity, and csnschools.io for more information about our courses. Thank you.
Hi Methods friends, how you going? This is Isaac Newton. Everybody knows Isaac Newton, the gravity guy, the apple fell on his head, you know the story. He's one of the most famous scientists and mathematicians that there is. So today we're going to be learning about a method that he came up with to find the roots of polynomials. But did you know that the Newton method is actually called the Newton-Raphson method? So who's Raphson? It turns out that Joseph Raphson not only discovered the method, but he made it better. He perfected it. And the way that we're going to be using it is the way that kind of Raphson perfected. So why doesn't he get any credit? In fact, I tried to Google Joseph Raphson and the only picture I could find of him was this. But then I put that picture into a Google image search and it's not even him. It's this guy. What's going on? There's heaps of pictures of Isaac Newton. Look at this one. Look at this one. There's even cartoons of Isaac Newton. What does Joseph Raphson have? The only thing I could find was his signature. Here's his signature. So, Joseph Raphson, we salute you. We remember you. We love you. I'm going to put your signature on every slide in this presentation just as a shout out. And it's the least I can do. We love you, Joseph. So the name of the lesson is Newton's method. You and I both know it's the Newton-Raphson method, but for the sake of brevity, let's go on with Newton's method and let's have a good time. So we're going to be looking at understanding Newton's method. What is it? How does it work? We're going to come up with a formula and we're going to be looking at how that formula is applied. Then we're going to look at how we can use technology, which is a lot simpler with Newton's method. And then we're going to look at the limitations because there are places and situations where it doesn't work. So let's get stuck in. So what is Newton's method? So it's an algorithm used to find approximate roots of functions. And when we say the roots of functions, we're talking about the x-intercepts. So the way that we do it, I've got a picture of a polynomial here. And what we do is we make a guess. We have a guess as to what the x-intercept is. So let's just say our initial guess, which we call x0. We'll get into that notation a bit more later. Let's say our initial guess is 3. So we're going to have a guess of 3. And we look at the y coordinate at 3 and it's 2. If it was the x-intercept, of course, the y coordinate would be 0. So we've had a guess and we've said, we think the x-intercept is 3 and we've plugged it in and it wasn't the x-intercept. So what we do is we use the tangent at that point. Now, at this point, if you have not done the calculus area of study yet, you may want to do that or have a look at that before you get into this lesson, okay? That being said, I'm going to kind of step you through it so it does make sense, I hope, without you having done the calculus area of study. But where were we? What we're going to do is we're going to draw a tangent where that first guess was. So here's my tangent. So if you look at that tangent, that green line there, if you look at where the green line is going, as we follow it down to the x-axis, that point there is a better guess of what the x-intercept is. It's a little bit closer. So what we do is we say that's going to be my next guess. So I'm tracking the guesses over here. My first guess for the x-intercept was 3. Then we found the tangent at that point, and we found the x-intercept of that tangent, and that becomes my second guess, which was 2.4285, and so on and so on. So what we do there is we want to come up with another guess. So we go, okay, I'm going to take that point there, 2.42, and I'm going to find the tangent at that point on the polynomial. So I find another tangent, which will look like this is my orange line. And as you can see, as I make successive guesses using the x-intercept of the tangent, I'm getting closer and closer to that true value of the x-intercept, which is 2. So you can see here, there's my third guess now, which is 2.1278, etc. And then we're going to draw another tangent. So there's another tangent, the purple line. You can see now we're getting really, really close with that x-intercept. And if I keep doing that, it will approach 2. Okay, so it will converge to 2. So that's the basic method. We're going to look at how to do it using a bit of calculus. And I hope you enjoy. So let's keep going. So the idea here is we're going to be using differentiation. Now, if you've got no idea what differentiation is, like I said, that's going to be in the calculus area of the course, but we're going to tackle it here. So we're going to look at this function, which is a cubic. And I've given you the rule for the cubic, x cubed minus 6x squared plus 11x minus 6. And we happen to know that the x-intercepts are at 1, 2, and 3. And what we're going to do is we're going to approach 3. we're going to use Newton's method to get close to the x-intercept of 3. So what we're going to do is I'm going to use an initial guess of 4, which is this point here. Okay, so that's the function at 4. Now we know the x-intercept is not at 4. So what I need to do is I need to get the equation of that tangent, and I need to find the x-intercept of the tangent. So to do that, I need to know the gradient at that point there. And to find the gradient at that point there, I need to differentiate the function. So the derivative of x cubed minus 6x squared plus 11x minus 6 is that there. That is the derivative, 3x squared minus 12x plus 11. And that is how we differentiate polynomials. We're only going to be dealing with polynomials in this lesson. In fact, we're only going to be dealing with cubics. So you should, if you've done the calculus area of study, you should know. If not, we take the 3 and we multiply it out the front here, and then we knock 1 off the power. And then the 2, we multiply out the front here, and the power drops to 1. And then the same thing here, we multiply by 1, and then the power drops to 0, and 11 times 0 is 1. So it's kind of what's going on here. Like I said, watch the differentiation videos if it will help you. So where are we? We've got the derivative. F dash of x is equal to 3x squared minus 2x plus 11. What I want is I want the gradient at that point 4. Our initial guess is 4. That's where we think the x-intercept might be, and of course it's not. So if we sub 4 into the function, so f of 4, we get the y-coordinate on the polynomial, and f of 4 is 6. So the coordinates of this point are 4, 6. And what I want also is the gradient at that point. So the gradient at 4 is 11. So what we know about gradients is that gradient is the gradient of the tangent. So there's my tangent. So the gradient of that dotted line, the gradient of the tangent is 11, which is the gradient of the polynomial at the point 4, 6. So what we know is that we know that gradient is 11, and we also know that this distance here is 6. So what I want, remember, with Newton's method is to work out that point there. Okay, that's my new guess. So it would be really helpful if I knew this distance here, because then I could just take the x coordinate, which is 4, and then just subtract that distance. So that's actually what I'm going to do. So remember that the gradient of the dotted line was 11. So that would mean that the rise over run is equal to 11. The other thing I know is that the rise, if you like, is 6, isn't it? Okay, is 6. Okay, so that would mean if I solve for the run, that would be 6 divided by 11. Okay, so this distance here, okay, or the bottom of my right angle triangle, that distance there is 6 on 11. So that would mean that my new guess, or this point here, just stay with me, that this point here would be equal to 4 minus 6 on 11. Okay, so that's going to be my next guess. So my first guess was 4. My next guess is going to be 6 on 11. So my x1 will be 4 minus 6 on 11. So 4 is 44 on 11. So 44 on 11 minus 6 on 11 is 38 on 11, which if you put that in your calculator is around 3.45, well, it's 4545 recurring. Okay, so getting closer to our correct guess, which is at 3. So let's have a look at what we did there, because we want to come up with a formula. We want to do that again, don't we? I'm not going to do it again because we don't have all day. But if I was to do that again, I'm going to now want to know what that point is there. So it would be 38 on 11, and then the y coordinate, which would be f of 38 on 11. And then I'd want to know the gradient at that point, which would be f dash of 38 on 11. And then I would do exactly the same thing. And what I would do is, if we look at what we did here, my 4 minus 6 on 11, let's go back to our first guess. Of course, the 4 was our initial guess, was our x0. What was the 6? The 6 was the y coordinate, so that was f of x0, and 11 was f dash of x0. So what we can do is we could then repeat that with our next guess. We could do, to get x2, it would be 3.4, actually, let's use 38 on 11, let's be exact. It'd be 38 on 11 minus f of 38 on 11. So the y coordinate at 38 on 11 divided by the gradient at 38 on 11. And what we've stumbled along here is the actual formula, which we will get to in the next section. But what I wanted you to see here is where that second guess has come from. So we've taken our first guess, which was 4. We've found the y coordinate there, and we've found the gradients, and we've used that, rearranged our rise over run to get this distance here, which we can then use to get the x-intercept of the tangent. And that's kind of how we do it. We keep repeating that over and over again. Okay, so I want you to take that away and look at where that's come from. So you can use your x0 minus f of x0 divided by f dash of x0, if you like, if you've got that jotted down. And we're going to use that in the multiple choice question, which is just about to come up. And then we're going to look at the formula and start applying it over and over again so that we can get really close approximations. I hope you're still with me. It's a real tricky lesson. Okay, time for you to have a go. Okay, so we're going to look at something now called the iterative formula, which we've actually already worked out. An iterative formula is essentially when each of our answers are generated from our previous answer, where we're repeating the algorithm over and over again. So we looked at calculating our first guess, after our initial guess, I should say, our first approximate guess using the formula. We're taking that initial guess and subtracting the y value at that point divided by the gradient at that value was the formula for that first approximation. Now, if we just extend that to be the nth approximation or the n plus 1th approximation, we're just using the previous one. Okay, so that's what we mean by that. So x of n plus 1, so let's say the 10th approximation is given by the 9th minus the y value at the 9th divided by the gradient at the 9th, and so on and so on and so on. So that's just how we represent it as a formula, because it's iterative. We're using a new value each time we generate a new guess. The good news is the calculator can generate many guesses at once for you, and we'll look at a couple of ways to do that soon. The other thing that's worth noting is that the closer your initial guess actually is, the faster the algorithm will approach the true value of the x-intercept. So if this was my first guess here, for example, then I'm already very close to 2, and my tangent's going to get even closer. Whereas if I guess something way out here, it might take me quite a few tangents to approach. Or if I guess something out here, then the tangent's going to be down here, and then it's going to maybe approach one of the different x-intercepts, or maybe it'll be all over the place and take a long time to get there. So, or maybe it won't get there at all, which is something that we'll look at later. Okay, I don't want to throw you too much. We're just looking at the formula now, and we're going to apply it. So let's have a look at a worked example. All right, so for this example, we're going to be looking at Newton's method to estimate the x-intercept of the function with this equation here, x cubed minus 5. Now, you should be able to tell me that if I set the function equal to 0, I can find the exact value of that x-intercept. It'll be the cube root of 5. So we know that, and that's great. So this method is a way to approximate this x-intercept. We can see how closely it gets to the true value of the cube root of 5. So we can also see that Newton's method can be used to approximate values for surds and things like that. So the cube root of 5, it's going to give me an approximate value for the cube root of 5 if I go far enough. The derivative of x cubed minus 5 is 3x squared. So what we're going to do, we're going to see here as we get x1 and then we get x2, the algebra, well, not the algebra, the fractions are going to get really, really messy, and we're not actually going to work it out all by hand. I'm just going to show you where the values would be generated, and then you can use the calculator to plug it all in, and I'll show you what the answer would be. But let's do the first one. So we would get that the first guess, because our initial guess is 3, our first guess would be equal to 3 minus the function at 3 divided by the derivative at 3. So if we sub 3 into the function, we get 3 cubed minus 5. which is 3 cubed is 27. So 27 minus 5. And then we get, when we sub 3 into the derivative, we get 3 times 9, which is 27. So it's pretty messy. 27 minus 5 is 22 on 27. So 3 is going to be, what's that? 3 times 27 is 81 minus 22 on 27, which is 59 on 27. So that's our first guess. And 59 on 27 is getting a little bit closer to the cube root of 5, but it's not there yet. So to get my second guess, and this is where we're going to plug it into the calculator. So 59 on 27 minus, we're going to sub 59 on 27 into x cubed minus 5, and then we're going to sub 59 on 27 into the derivative, which is 3x squared. And when I do that, I get a horrendous looking number, 509,173 divided by 281961. So of course we would never do this by hand. That is roughly 1.8058. Now the cube root of 5 is 1.70997, etc. So we're getting close. If we do 2 more iterations, if we get to around x3, x4, we're getting very, very close to the true value of the x-intercept, which is 5 to the power of a third. So there you go. That's how we can generate a couple of guesses. So I'm going to get you to have a go, and then let's get the calculator involved even more. So your turn. Okay, so let's get out our friend the calculator. We really need it in this lesson because we are struggling with some of these fractions, some of these work examples. So no more, calculator is going to take over. And this is how we can generate many estimates using Newton's method. So we're not going to find x1, then x2, then x3. Let's just get the calculator to do a bunch at once. And there's a few ways to do it. I've just shown a few screenshots of the Casio class pad here. Essentially what I'm doing here is I've found my first guess. So the initial guess was 3. So my first approximation is 2.57. And I've set that up with as a x minus the function divided by its derivative. And then given that x equals 3, because then I can just go, all right, do that again, given the answer, and it'll plug the answer in and it'll keep doing that. And there's my next guess. Of course, I could define it as a function then, because then if I do f of 3, that will get me all the way to this third approximation in the one step. And the other way, the way that I think I'm going to do in the work example shortly, is to use a sequence. So there's a sequence function in the calculator, in the class pad, and I can actually set up my iterative function in here and then use my first guess of 3 and then generate a whole table of values so I can look down. And that third method, this method using the sequence here, is really useful for questions like where it'll say, how many times do I need to repeat the algorithm to get the root within 2 decimal places, or get it correct to 4 decimal places, or something like that. Because then I can just look down and get my answer. And we're going to look at one like that shortly. But before that, let's look at some pseudocode. This is a really good part of the course to use pseudocode because we're applying an algorithm and we can use the programming in the calculator. We're not going to look at a program in the calculator. We're just going to look at one way to represent this using pseudocode. So we can have our input as the function and x0 as our initial guess. So we're defining a function. We're getting the calculator to repeatedly apply the algorithm. And what we've done here is we've told the program to stop when you're within 0.001, or when your next guess is within 0.001 of your previous guess. So in other words, my repeated, my x10, my x11, my x12, it's barely changing, which means we've gotten really, really close to the correct value of the x-intercept. So we've told the program to stop at that point, which we could call the tolerance level. So a tolerance level of 0.001, okay? We are going to look at a question on this. If a lot of that is gobbledygook to you, don't worry too much. We just need to be able to interpret it. And you'll see in the question, I hope that it's not too bad, okay? So stay with me. But let's look at a worked example first. Okay, so let's have a look at a worked example, and eagle-eyed viewers will notice that this worked example is the same one that we did earlier that got rather messy. So now we're going to use the calculator to help us out. The question's slightly different though. So we're still approximating the x-intercept of the function, which of course is still the cube root of 5 is that x-intercept. This time we want to find the value of n, where xn gives the first estimate that correctly approximates the intercept to 5 decimal places. That sounds really hard, doesn't it? So the first thing we want to do is work out, well, what is the x-intercept to 5 decimal places? What am I trying to get to? So the first thing I would do is work out what the cube root of 5 is. To 5 decimal places, it's 1.70998. Okay, now let's look at how we can use the calculator to see the first time our approximation would round to 1.70998. That's what it's asking us to do. Okay, so we got this, come on. Okay, so before we get into our sequence, we can see here that we've solved the function equal to 0 to get that 1.70998 if we didn't know it was a cube root of 5. So let's look at our sequence. So we're in the recursive section here. We're going to use an plus 1, and we want to set up our iterative formula, if you like. So we're going to use an, so the previous answer, minus, and then we want to use f of x divided by f dash of x. So I'm just going to plug it in terms of an, which is our x, if you like. So I've got, let's see, an cubed minus 5, and that's going to be divided by the derivative, which would be 3 an squared minus nothing. So there we go. Now our initial guess is what we put in here, which will be 3. And now we're going to generate some values. So, whoops, we'll click, make sure that's clicked, and then we'll generate some values. So you can see here, there's my first, there's x1, x2, x3, x4, x5. Now, because it's rounding it off here, I might need to actually select on here to see which is the first time that we've correctly got our answer to 5 decimal places. So we need to go down to 1.70998. It looks like this one here. So the previous x4 gives me 1.70999. So x5 gives me 1.7099975, which would correctly round to 5 decimal places. So the answer to the question is that n equals 5. Okay, pretty tricky. If we've got all the data here in front of us, we can kind of work out what we're trying to do. I hope you're still with me. Let's have a look at a question for you. Okay, so let's look at limitations of Newton's method. So there's a couple things to look at here. First of all, there are cases where Newton's method will work, but it'll take a really, really long time to approach the solution. We're not so interested in that. I want to look at times where it just doesn't work at all. So the first case will be, I'm going to look at a function here. Let's just have a look at what happens before I tell you why it happens. So we're going to use this function here with an initial guess of 1. So the derivative would be 6x squared plus 6x minus 12. My first approximation is going to be 1 minus, let's see, so 2 plus 3 minus 12. When I sub in 1 over, when I sub 1 into the derivative, I get 6 plus 6 minus 12. So what do I get? I get 6 minus 12, negative 6 on the numerator, and I get 0 on the denominator. So that's undefined. So x1 does not exist. Okay, it's undefined. So why did that happen? The reason it happened is if you have a look at the function, at the point 1, that's it here. Okay, that's a turning point. If you draw a tangent at that point here, it's parallel to the x-axis. So it doesn't hit the x-axis. I can't find the x-intercept of that tangent because it doesn't have one. So this case of where Newton's method doesn't work is if my initial guess happens to be a turning point, then it doesn't work. So that's why I was talking about how when we make our initial guess, we should try to make sure that it is somewhat near the x-intercept. So if we kind of just guess wildly, we might accidentally guess something that's a stationary point, in which case we won't be able to find the next guess. So that's one case of where Newton's method doesn't work. Let's look at another one. So this case, I'm going to use this function here, and I'm going to use an initial guess of 0, and then we'll have a look at why it doesn't work. To save a bit of time, I'm going to use the calculator here. So let's have a look at what happened. So I set this up on the calculator, and my initial guess, so I've subbed 0 into this function here. So 0 minus, we've got 0 in the function divided by 0 in the derivative. And my x1 was equal to 2. Now, if I use 2 and I sub that in, my x2 is 0. So hold on. Then if I obviously put 0 in, I'm going to go back to 2 again. So that's why we call it an oscillating sequence. So what's happening here, you can see I'm going to go 2, 0, 2, 0, 2, 0. It's not going to converge onto anything. Newton's method is not going to approximate a root because it's just going to keep bouncing between 2, 0, and 2. Now, if you have a look at the graph, let's have a look at why this happened. So our initial guess was 0, which would give me this tangent here. And when I found the x-intercept of the tangent, it was 2. And then when I found the x-intercept of that tangent, it went back to 0 again. See how these tangents are parallel? So it's just going to go round and round and round and round in circles, and it's never going to approximate this root or this root or this one. So it's not going to work. So that's another example of a limitation of Newton's method. It's not as common as that first one, but it is a limitation nonetheless. So let's have a look at a question for you. Okay, so to sum up the lesson, we've been talking all about Newton's method, which is an algorithm that we use to find approximate roots or x-intercepts of functions. We've only looked at it for cubic functions because that's what's in the study design. It does work for other functions as well. So you might like to have a go at it with a quadratic or a function that's a little bit simpler for plugging things into the formula. Speaking of formulas, we developed what we call an iterative formula for Newton's method, which is where we generate each guess from the previous approximation. So xn plus 1, so the n plus 1th guess is equal to the previous one minus the y coordinate at that point divided by the gradient at that point. Again, if you need to look at the calculus area of study first and then come back to this lesson, it will hopefully make a little bit more sense. I hope that you're able to apply this formula now. Of course, we can use technology to generate multiple guesses at once, multiple approximations, and see what we're getting towards. Often our questions are about how many iterations will it take for me to get, this close to whatever the real value of the x-intercept is. And of course, we know that Newton's method works best when we start with an initial guess that is quite close to the true value, so we're not zipping all over the place. Okay, so that's it for this lesson. I hope you've enjoyed the little shout outs to Joseph Raphson. I know what you're thinking. If I love Joseph Raphson so much, why didn't I call this lesson the Newton-Raphson method? And it's actually a good question. Why didn't I do that? Can I still do that?
Please, just end the lesson already.
Sorry. And see you next time.